Hello everyone. In this presentation, we introduce ApproxNet, a video object classification system for embedded clients, which is specifically designed to adapt to content characteristics, resource contention, and varying users' requirements. My name is Ran Xu, and this is a joint work with Rakesh, Pengcheng, Peter, Ganga, Shumali, Subata, and Saurabh. First, let me introduce the background of our vision system. We focus on the object classification system for streaming videos on embedded clients. This can be used in many cases, for example, a surveillance camera detecting airplanes in the scene, or a camera in the wild capturing and detecting antelopes in the national park. The common requirement for such systems are streaming and on-device, meaning that video frames are expected to be captured and processed at 30 frames per second in the real-time manner. The object classification for every frame are needed, and the algorithm should not refer to the future frame as they are not available at the time of execution. Execution are expected to be on the device, which is typically an embedded board or a mobile-like device with limited computational resource. Researchers and developers in the computer vision area have proposed many solutions for image or video object classification. Nowadays, convolutional neural networks are the main solution, and top 5 errors have dramatically reduced over the years on the ImageNet dataset, which is one of the most widely used classification and detection datasets. Especially, we look at the ResNet solution, which is the winner solution at the year of 2015 with the highest impact over the years. ResNet has several variants, either 18 layers, 34 layers, 50 layers, and more. A general intuition is that the more layers lead to a higher accuracy. Recently, many more models are proposed with deeper and deeper neural networks, achieving higher accuracy. However, we especially care the efficiency of the models on the embedded device to achieve the real-time 30 frames per second speed. So, some approximation must be done to improve the efficiency at the cost of reduced accuracy. One main motivation of ApproxNet is that when we look at the SOTA image or video classification models, for example ResNet, we found that video frames of different complexity category are best suited for different model configurations. For example, for a simple video frame, either using a computational heavy configuration or a light one do not make any differences. While for a complex video, we indeed need a deep model with a larger input resolution to correctly classify the frame. The main challenge of ApproxNet is the dynamic runtime conditions, including varying content characteristics through the video stream, resource availability on the device, and users' requirement. So, an adaptive model or system should lead the accuracy-latency frontier in all conditions. To meet the need of switching between configurations, we categorize the solution into a one-model design and a multi-model design. A one-model design means a tunable model with some knobs controlling its operation points on accuracy and latency, while a multi-model design typically uses a collection of models and model variants and switch between them, for example ResNet, VGG, and MobileNet, and each may come with several variants as well. Apparently, a multi-model design is straightforward, but considering the switching cost between configurations, we consider the one-model design as one of the top priority, and it is a challenging task to design, train, and optimize such DN with tuning knobs enabled. Given all these challenges, we propose an end-to-end system solution to address the problems. Given the input video frame in the streaming scenario, we design approximation-enabled one-model DN and call it the executor. The executor comes with many execution branches which can independently run and classify the video frame. We then design a scheduler which decides which execution branch is the optimal one that satisfies the user requirement. The scheduler comes with a frame complexity estimator and a resource contention estimator to handle runtime conditions. We will discuss these two in detail later. To further reduce the cost of such online scheduler and estimator, we design an offline component, a profiler that collects the accuracy, latency, and switching overhead profiles and serves the online scheduler. In this work, our contributions are in three folds. First, we design, implement, train, and optimize a one-model approximation-enabled DN. Second, we design an end-to-end system that can adapt at runtime to varying content characteristics, resource contention, and usage requirements. Finally, our system is specially designed with low overhead and achieves accuracy latency frontier with the overhead considered and included. Let's dig into the design details. First is our approximation-enabled DN. The design principle is that it must be more efficient to be able to run with 30 frames per second on the embedded device. Be accurate since we do not want to sacrifice the accuracy too much. Be adaptive so that we can use it for dynamic conditions. And with low switching costs to seamlessly switch between configurations. So we design two tuning knobs. The first one is the input shape, which means how we resize the video frame and fit into the neural network. And the other is output, which means at which layer we want to get the classification results. And intuition is that smaller shape and early output can improve the efficiency at the cost of reduced accuracy. Note that normally such DNs does not require a dynamic input shape and output at any intermediate layer. So we especially design our DN with these features and train our approximation-enabled DN so as each approximation branch can independently run, all with comparable accuracy. We name the choice combination of a certain shape and output as an approximation branch, and we have 30 branches in our design. Given so many execution branches, we define the Pareto frontier branches as the branches standing on the accuracy latency frontier. Especially, we should be careful that such Pareto frontier branches are not static. This means the latency of each branch depends on the resource availability on the device and may vary differently under resource condition. The accuracy latency frontier also depends on the content characteristic, as the video frame of different complexity category may have different accuracy. So, to make the system content aware, we design and implement a frame complexity categorizer. We use the age feature as the indicator of the frame complexity, and each frame complexity category comes with its own Pareto frontier branches. For example, in the figure on the right side, we show frames in 4 different complexity categories. We also study how our system should adapt to resource contention. First, we need to emphasize that we treat the resource contention from other applications and the operating system as a black box and as a whole. This choice has 2 advantages. First, we do not need the system privilege to know the context of other applications, as the privacy, especially on mobile and embedded devices, is another important issue. And second, we ease the problem with 2 components, ApproxNet and the outside world. ApproxNet only needs to adapt to the resource contention from the outside world and thus can adapt to any known or unknown and any combination of resource contentions. To achieve this, during the offline phase, we use benchmarking tools to generate the synthetic CPU and GPU contention to ApproxNet and measure the latency of ApproxNet under contention. During online phase, we monitor the latency of ApproxNet and estimate the level of contention and further adapt with optimal branch under such resource contention level. Finally, the scheduler as a core component to make the decision on which branch to run solves an optimization problem of picking optimal branch, which is subject to the accuracy target A tau, with content-aware accuracy A of branch B in content capacity category F, and contention-aware latency L of branch B in contention category C. The switching costs and system costs are also included so as the total latency is minimized in our solution. Especially, we want to emphasize 3 key design elements in our system to reduce the system overhead. First, our one-model approximation-enabled DN minimizes the switching costs between branches since we do not need to reload any component of the model. Second, we reduce the overhead of the scheduler by offline profiler. Finally, we reduce the overhead of frame complexity categorizer with a scene change detector, in which only when the scene in the frame change large enough do we recalibrate the frame complexity category. Otherwise, a category memorizer takes the past category as a proxy. We evaluate our approximation-enabled DN on LSVRC image dataset with the image classification task and our entire system on the LSVRC video dataset with the video object classification task. We use NVIDIA Jetson TS2 as our evaluation device. For ApproxNet and the compared baselines, we mainly report three metrics: the top 5 accuracy on the test dataset, the per-frame latency of the DN, including both the execution time of the DN and the system latency overhead. We compare ApproxNet with a total of 5 baselines, represent of 2 variants of 18 and 34 layers, MCDN as a collection of light and heavy model variants, MSDNet as a multi-scale DN, MobileNet as an efficient DN, and NetDN as a multi-capacity DN. We show the accuracy versus latency trade-off of the DN component on the image dataset on the left figure. We can see that ApproxNet has the adaptive accuracy latency frontier between 15 and 40 millisecond latency on the embedded device, while ResNet and MSDNet cannot meet the real-time processing speed. MobileNet, though being more accurate at the same latency, is a collection of model variants and will suffer from the large switching overhead. In the right figure on the video dataset, we study 3 typical usage scenarios: a low latency, low accuracy, medium latency, medium accuracy, and high latency, high accuracy scenarios. We can see that ApproxNet is much faster than MCDN with the similar accuracy. MSDNet again cannot meet the real-time processing speed, and so do MCDN models. Further, we examine ApproxNet in each frame complexity category. We observe that ApproxNet provides complexity category-specific approximation branches which satisfy 30 frames per second latency requirement and maximize the accuracy, while ResNet of either 18 or 34 layers cannot meet the 30 frames per second latency requirements. We evaluate ApproxNet under resource contention by manually injecting the synthetic CPU or GPU contention and observing the temporal latency. We can see that in the left figure that we test with 4 phases with varying CPU conditions. ApproxNet shown in the blue curve has latency below 33 milliseconds, while MCDN has much increased latency under larger CPU contentions. The same trend holds as we inject different levels of GPU contention in the right figure. Finally, we show that ApproxNet is superior in terms of lower system overhead. In the left figure, we can observe the latency spike at the time of switching in the MCDN baseline and not in ApproxNet. In the right figure, we show that the overhead of ApproxNet is negligible but takes a big portion in MCDN. We especially look at the switching overhead between execution branches in ApproxNet and compare with NetDN, which also has a similar multi-capacity DN. We show that the switching overhead of ApproxNet is mostly below 10 milliseconds, rarely at 10 to 30 milliseconds, while NetDN comes with 5 to 25 second switching overhead as we switch from a low capacity model to a high capacity one. To conclude, as the era goes fast, there are better models and devices, new applications, and new users' requirements. We want to emphasize the key design methodology as takeaway messages, since they can apply to a new context and various domains. The first is the one-model approximation-enabled DN, which targets at higher efficiency on the device, high accuracy, wide adaptability, and low switching overhead. This is the enabler of our system and is different from many vision models. Second is our end-to-end system design to adapt to runtime conditions. Particularly, we use a frame complexity categorizer to determine the content category and contention sensor to determine the contention level. Depending on the application and device, these two modules can vary, and other feature models can also be considered. On the other hand, the scheduler picks the Pareto frontier branches to minimize the latency at any desired accuracy level. Finally, our design to reduce system overhead is also a successful factor that one should not ignore. Particularly, a one-model DN reduces the switching cost, the offline profiler reduces the cost of online scheduler, and the online scene change detector reduces the cost of online estimators. We hope our experience on the video object classification system can also help the design in many similar vision systems and broadly approximate systems. Thanks for listening, and I'd like to take any questions.